Hello, everyone. Let's get started. For some of you, welcome back from Informs. I mean, for partying, we should actually get to work now. I'm still struggling to get out of the Informs partying mode. So it's a pleasure to have Neil visiting us from Durham. So Neil is a professor in operations management at Durham University Business School, where he's also a deputy head of the Department of Management and Marketing. Neil got his undergrad, master's, and PhD, all his degrees in mathematics at University of Cambridge, and he broadly works on applied probability and his primary interests are on decentralized congestion minimization in networks. But more recently, he has been also working in learning bandits, reinforcement learning, stochastic approximation, and so on. And before Durham, Neil has held several positions at University of Amsterdam, University of Manchester, Microsoft Research Cambridge, ETH Zurich. He also was a fellow of the Alan Turing Institute and a guest lecturer at London Business School. Neil is currently the area editor for stochastic models at Operations Research Journal, and he's associate editor of Stochastic Systems. Neil has won several awards, including the ACM Sigmetrics Best Paper Award and the Erlang Prize in 2018. Today, he's going to talk about exponential tail bounds for stochastic approximation. So without further delay, Neil, the floor is yours.
Thanks for having me. It's great to be here. I'm very excited. I even got my AI4OPT sticker.
Oh, wow. I don't have one.
So, pick one up, yeah. So great to be here. Yes, so this is the talk about stochastic approximation, particularly stochastic gradient descent. Usually in stochastic gradient descent, there's some sort of quadratic function that you reach at the bottom, and then the kind of estimation bounds you get there give you some sort of Gaussian tail bound. I'm kind of interested in the case where it's not like that, where it's kind of sharp, some sort of pointedness when you reach the optimum. And then I'm interested in establishing what are not Gaussian tail bounds, but what are going to be exponential tail bounds in that case, turn out to be the correct approximation or sort of limit behavior for those systems. Okay, so that's the main topic of today. Before I do that, I wasn't quite sure how to position this talk, so I kind of thought I'd just kind of flash by a few other kind of research topics I'm interested in, and I'm going to be here for the week, so if anything interests you, then feel free to come chat with me. As Steve sort of alluded to, my main interest is in queuing systems, really. So this is slightly different to my usual research area. I'm quite interested in running AI4OPT. I'm quite interested in learning for queuing. So some sort of theoretical works a little bit in that direction. On the applied side, I've worked on kind of reinforcement learning techniques for traffic signal control. And here's some sort of algorithm that we developed using deep reinforcement learning. And here's a kind of one of the main commercial systems used in the UK. So we've kind of been interested in, well, at least in the past, in kind of developing that kind of stuff. I also have a contract. Well, I was previously at Manchester University, and I have a contract with the NHS Hospital Trust there with about 10 different hospitals. I've been working on patient scheduling for operations, not operations research, but operations, with a surgeon. I've recently started working a little bit on quantum computing with a company in Cambridge. So I've got some interest in that area with a colleague of mine in Durham. In Informs, I was talking a bit about revenue management, but where there's revenue management with some sort of queuing or inventory control system in the background. So things where you're trying to learn and optimize at the same time, but with some Markovian behavior happening. The two co-authors I mentioned are Kody Law and Shangda Yuan. So Kody is a colleague of mine. We co-supervise Shangda. Kody has just spent the last year working on a Meta's AI groups, and so we've been working on a project in Bayesian optimization. So there, you essentially want to try and learn. Usually, you have to choose an acquisition function to try and do some sort of continuous bandit type problem to learn the optimum of some function, and we've come up with some Monte Carlo methods that are essentially faster than what you typically use in PyTorch, which is the main architecture you would use in Facebook. So that's the result saying that our system works nicely. I probably would have talked about that today, but it's still a little bit, we're still writing up proofs and doing that kind of stuff. If we're interested in that. Okay. Right, so that's sort of some other stuff that I'm interested in. If anything there's of interest in, you want to have a chat, just come have a chat with me. Now on to the talk. So a bit of an outline. So I imagine there are people in the audience who know much more about these things than me. I'll give some discussion on stochastic gradient descent, in particular projected stochastic gradient descent. So that's where you're trying to constrain yourself to belong to some potentially bounded set or just some set of convex set. Okay. And as I mentioned at the beginning, typically the focus is in stochastic gradient descent and also stochastic approximation. Is often normal distribution concentration bounds. And here we're going to be doing something slightly different, looking at exponential concentration bounds. And like I say, I'll explain why the sorts of ideas coming in here come from someone who's a kind of queuing theorist by training, and why sort of queuing theory can help provide some intuition for why exponential distributions are happening here rather than normal distributions. So I'll give it a little bit of that intuition. Then continuing, we'll give sort of theoretical results. I'll present a sort of general result for some general stochastic iterative process. Then I'll give a specific case of that where we look at projected stochastic gradient descent, which is sort of the most vanilla algorithm that you could consider. I'll give a proof based on some other works that we kind of submitted this paper, and they came back to us and mentioned this paper on linear convergence for projected stochastic gradient descent. So you can actually get linear convergence that goes down exponentially fast with a certain probability, and you can prove that that's much faster than you typically get with stochastic gradient descent. It's possible to achieve that in this case where you've got this kind of sharp function. So there's kind of a new proof, and we improve on some prior results with the concentration bands that we come up with here. Okay, and we'll explain that although we get exponential concentration rather than Gaussian concentration, we don't have an exponential limit. Okay, so typically in stochastic average approximation or stochastic gradient descent, the limit object of the iterates is a normal distribution. You can prove that. I guess will be if you're getting exponential tail bounds here, then it should be an exponential distribution. Yeah, we'll show that's not true. Okay, it could be a general set of things. Okay. And that's important because, you know, in these kind of normal approximation results, the kind of this notion of kind of Lecam and Hajek have these kind of asymptotic efficiency results relating to the kind of Fisher information. And what this is essentially saying is you're not going to have some simple Fisher information for these types of problems, essentially. Okay. Right. And I'll discuss some conjectures around that. Finally, I'll kind of wrap up a bit with some results on linear programming and RL. I probably won't talk about the Bayesian optimization stuff, and then I'll just kind of, okay, that's a kind of outline talk. All right, so I'll start with this slide. So a little bit busy, so I'll use my highlighter pen here. So we're going to want to solve some optimization problem, okay? We're going to minimize some function f of x over some set x, which we'll assume is some convex, compact, closed, with an open interior set, something like this. Okay, and in general, what we're going to do is going to create a sequence of iterates where x of t is going to be updated to x of t plus 1 by some change c of t, which we think of being something with, say, bounded variance. Okay, and then we're going to apply some learning rate to this. Okay, which is then going to kind of slow down the kind of average iterates that we're going to be taking. And the hope is that this sequence of iterates x of t are going to approach the optimum or the minimum of this function. Okay. And the prototypical example is where c of t is some noisy estimate of the gradient of this function. Okay. And in that case, we'd have regular stochastic gradient descent. Okay. All right. But I'll keep this fairly general for now. In general, what we're hoping for is that there's some negative drift in expectation. So we have something of this type, that the change in the function values is at least approximately here, minus the step size some sort of gradient. Okay. And that gradient might have a little bit of extra error in it, but essentially, you know, that's going to give us some negative drift. It's going to take us to the minimum function. Okay. And I'll add that, you know, there's a whole load of AI algorithms. I mean, you know, you could argue that like a decent chunk of AI and machine learning is just coming up with fancy algorithms that build on stochastic gradient descent, you know, sort of say good like 30%, let's say at least. Okay. So anyway, these iterates x of t we're hoping are going to go to the minimum of this function. Okay. And usually when the problem's smooth, okay, the gradients of this function, or the gradients of the iterates as we get closer and closer to the optimum, are going to go to 0. Okay, that's usually what happens. But we don't want to understand that case. We want to understand the case where actually maybe the gradient stays above some value delta for all points. I mean, there might be a subgradient that's 0, but everywhere away from the optimum, we're assuming we're kind of going down like this, or it's flat and like a ReLU function or something like this, it goes in at some angle. Okay? All right? Okay? And like I say, this is sort of just the general sequence of iterates, so we'll make general assumptions on those. Though in the back of your mind, you should be thinking of projected stochastic gradient descent, or just stochastic gradient descent, but where you just project it back into set X whenever you need to. Okay? Right? Is that reasonably clear? Yeah, sure.
Just wanted to understand how stringent this negative drift condition is, because, for example, if you do just gradient descent on a non-smooth, non-strongly convex function, then it doesn't like get closer to the optimum strictly in every time step.
Yeah.
So this is kind of saying that every time step you are making some progress.
Yes, that's correct. Yeah. So typically when you have convexity, you're sort of assuming, or some strong convexity, you're assuming some positive movement. Here we're going to not be assuming convexity of this function f, but we're going to assume that you could always make some positive progress at each step. Yeah.
But even like, for example, gradient descent or something like that wouldn't satisfy this condition in general. Like if you don't have f to be smooth, then probably it wouldn't.
If it did that, you might get stuck at some local minimum, I guess.
Let's say it's convex but not smooth and strongly convex, then I think it doesn't necessarily make progress every time step.
The iterates themselves might not make progress at every time step. It should be usually that the expected value of the iterate, so there's an expectation in here.
Okay.
Which is then in expectation making some progress. So it could jump back. But it's like a random walk with drift. The drift is negative. Yeah. Okay. So just explain briefly what projected stochastic gradient descent is. This is the kind of simple one where we have our function f. And what happens is we take our value x of t, and then we have some sort of noisy cost or noisy gradient estimate c of t, where the expected value of c of t at time t is just the gradient of the function here. Okay? And what we do is we just apply some factor alpha to this, minus it from our iterate x of t. If we're unlucky and we go outside of our constraint set x, then we just take the Euclidean projection back into the constraint set. There could be other projections, but let's just say Euclidean projection back into the set. And that gives us our next iterate. Okay? So that's pretty sort of standard gradient descent type algorithm. Okay, and like I say, because we're considering functions where the gradient doesn't go to 0, here are two kinds of cases that are going to happen. So we can have a thing where the gradients, I mean the iterates x of t are going to sort of jump around in a sort of noisy fashion. They might hit the boundary of our constraint set potentially. Whenever that happens, we might jump outside or we get projected back in. Okay, and then notice if the gradient, the average gradient is pointing in this direction, okay, we're going to have something where the gradient doesn't vanish. Okay, and the optimum is at the corner point. Okay. So like a prototypical example there would be like a linear program, yeah, where the objective of the linear program is noisy. And pretty much every linear program with a noisy objective function is going to be on extreme point. So you can expect this kind of behavior to happen pretty much for every linear programming task. We come with a stochastic objective function. We also consider functions like this, where it's sort of got a kind of pointedness. So we're not so worried about the constraints at x here anymore. As in, most of the time, we're actually not going to need to project. But still, nonetheless, the gradient's not going to 0 as we get down to the optimum over here. Okay? So it's not like kind of bowl-shaped quadratic at the bottom. Okay? All right. Like I say, typical machine learning analysis looks a bit like this. You take essentially the square distance between your iterates and the optimum. Do kind of a Taylor expansion. Okay, and then we've got some interpolating terms here that we can interpolate, and then we can apply convexity to this guy, and that's the usual way that the proof of convergence goes with stochastic gradient descent. Okay, And also there are variants of this. Online convex optimization will make a slightly different interpolation, but essentially comes to the same conclusion. Okay. Right. And here's a kind of typical example of projected gradient descent. I've got this function y equals x plus 1 squared. And we just apply stochastic gradient descent to it with a reasonably small step size. And here's the kind of density of the iterates with a fixed but small step size. So that's the gray bars here. And then we've obviously fit that to a normal distribution. And you can see it very closely matches a normal distribution. Okay. As the step size alpha gets smaller and smaller and smaller, we should expect the behavior of the iterates around the optimum to look more and more like a normal distribution. Okay. Why is that? So here's sort of some intuition. If it's locally quadratic, then essentially the drift here is always proportional to the distance from the optimum. Okay. So it's sort of like proportional drift, but with noise. Okay. And the main system that for a stochastic differential equation, which has proportionate drift and noise, is called an Ornstein-Uhlenbeck process, and the stationary distribution of Ornstein-Uhlenbeck process. Okay, so essentially, it's kind of picking up the stationary behavior of this stochastic differential equation, which is approximating what the what the iterates are actually doing. So and there's a whole textbook of Kushner and Yin where they discuss about this kind of behavior. Yeah, so that's sort of well known. This is an Ornstein-Uhlenbeck process. It's an appropriate diffusion approximation of the stochastic approximation algorithm. The stationary distribution of that characterizes the normal distribution behavior of the limit object. Okay. Okay. And so yeah, basically because of the stationary distribution of this guy, it's possible to argue, and I've made a slight mistake here, that alpha t should be over here. This approximates a normal distribution in the limit. Okay. Right. That's very well known. What we're interested in is the following setting. So now I've taken that same function, but now I've constrained it at 0. I said, do the same iterates, but you're not allowed that 0. I'm just going to project it back every time it happens. Okay. And here you see, instead of fitting a normal distribution, we've got a nice fit to an exponential distribution now. Okay. Okay. So what's going on here? So this is something that a queuing person will be very comfortable with. Essentially, when we've got this kind of non-vanishing gradients and the step sizes are small, this same process now, rather than having a drift that's proportional to the distance away from the stationary point, it's actually just going to always be positive. Okay, so you're going to have the same Brownian noise, but then a constant drift, because the drift always has to be bigger than, in this case, the drift is always bigger than 1, and actually 1 at the point here. Okay, that's a well-known object. It's called in queuing, or well, in diffusion stuff, it's called reflective Brownian motion. Yeah. We know the stationary distribution of reflective Brownian motion is an exponential distribution. Okay, so and that's a very common limit object in queuing, because a queuing process is essentially something with 0 and a noisy random walk, and we know that loads of queuing systems have this exponential tail behavior. Okay, right? Yeah.
Why is it not truncated Gaussian? Because if you go away from 0, then your drift is getting bigger and bigger.
Yeah, but we're going to be letting that step size get smaller and smaller. So really what we're doing is like a Taylor approximation of the derivative at this point. Yeah. Yeah. But indeed, like the macro level behavior is actually going to start to be impacting. But the limit where we let alpha go to 0, really we're just picking up that gradient. Yeah. Okay. So what we're interested in, and again I've made a typo that alpha should be over here. To what extent can we say that the sequence of iterates minus the objective here is behaving like an exponential distribution? Okay, that's sort of the main thesis of what we kind of want to study. Okay. Okay, so that establishes our main bound or main aim. Our aim is to establish release exponential concentration bounds, or something characterizing that exponential behavior, for things like projected stochastic gradient descent when the gradient is vanishing. Okay, and we want to explore some implications of these concentration bounds. Okay, that's the aim for today. Yeah.
So why don't you get any probability mass on 0 in the previous picture? Because when you check the back,
Yeah, you're correct. There is probability mass on 0 in there. I've just cut that off. So yes, you're completely correct. If I was to completely draw the picture, there'll be some positive probability of being at 0,
right.
and then there'd be this exponential behavior. So I've kind of just cut that off. But it's a great observation. Yeah, so typically, like with the queuing systems, the behavior of 0 is actually different than the behavior. We write a positive proportion of the time in this example, not in all examples, but in this example, positive proportion of the time will be 0. But the probability that you're moving away from that optimal, the probability of when you're moving away from that is still going to have this exponential tail behavior. Okay, great question. As I kind of alluded to before, from a queuing perspective, the idea of random walks and reflection and exponential concentration, they occur all the time in queuing applications. So the kind of point is, can we use some of those ideas here to help us prove these kind of concentration bounds? Okay. So here's kind of a bit of queuing kind of 101. So a prototypical queuing example would be the GG1 queue. Okay, so here we imagine x of t being the amount of work in a queue. Okay, and this is the amount of work just before an arrival happens in that queue. All right, so imagine I've got some queuing system with the server at the front. The server sort of draining liquid or the work out of the system, and we're looking at the point just before an arrival occurs and some extra work gets added on. Okay. So what happens here is x of t, okay, the amount of work just before that arrival happens. We get the work that's added on from the arrival, and then we get some waiting time between now and the next arrival where the server drains out some of the work. And that takes us to here. Okay, and then that gives us the next time just before an arrival happens and the amount of work that's going on. Okay, and we can write that down as a recursion. Okay, this is known as the linearly recursion. It's basically, we just add the amount of work that's arrived minus the amount of work since the last arrival. And the only slightly difficult case is where if we hit 0, we actually just stay there. We don't sort of drain into having negative work in the system. Okay. And you can think of that as a kind of prototypical example of that picture that I drew earlier. It's just a projected stochastic gradient descent here with a projection of 0. Okay, so it'd be like the simplest projected 1D projected stochastic gradient descent with non-vanishing gradient. Okay. And it's very well understood recursion here. Okay. If this data here is kind of IID, you can use the optimal stopping theorem to prove an exponential concentration bound. That was proven by Kingman in I think 1950s even. Okay. And there's also a bound called Kingman's bound. Okay, where you can analyze the stationary behavior of the GG1Q, and you can bound it above by the variance of the movement here, divided by the net negative drift of this random walk here. Okay? And the thing you'll notice is that if this was indeed something like a projected stochastic gradient descent, a very simple projected stochastic gradient descent, and if I let alpha be my step size here, then the variance here will be proportional to alpha squared, and the drift will be proportional to alpha. So the net error would be of order alpha. Okay, so it'd be proportional to the step size. And I'll say that that's different to what you would get if we didn't have that vanishing gradient. This would be square root of alpha. Okay, so you'd have a slower rate of convergence, you'd have a bigger error. Okay? Yeah. Right? So essentially when we've got this non-vanishing gradient, then we're going to expect a higher level of concentration, which makes sense because the drift doesn't go to zero anymore. So it makes sense it's more concentrated. But what Kingman's bound tells us is what that concentration level is. Okay, so it's actually alpha. Okay, right. So now we've got some intuition from sort of queuing theory as to what the rate of convergence is going to be, and we need to kind of go about proving that is correct. Yeah.
So we have like alpha instead of root alpha mean, but then exponential tails instead of Gaussian tails.
Yeah,
So
correct.
like the long-term tails look similar in the two cases.
Well, the variance would still be kind of going up, so it'd be like it would still be significantly more concentrated with its exponential
No,
concentration.
I mean like very different tails because Gaussian have quadratic tails versus linear tails.
Yeah. So basically, the mean and the variance of the Gaussian is bigger.
Yeah.
It's a light tail distribution.
Right.
Whereas here, it's an exponential distribution that's much more concentrated, but it's a heavier tail.
Okay.
So how do we generalize this? The result we use is from this paper by Hajek in 1982. Okay, so he has this great result, this sort of Hajek bound, which is a result for Markov chains, not for stochastic approximation, which you can use to get these kind of exponential concentration bounds. Okay. So what does Hajek prove and why does he prove it? So the idea is you have a Markov chain and you want to prove that it's exponential or geometrically ergodic. Okay, so sometimes when a Markov chain is ergodic, you want to prove that that kind of goes down to some power, the difference between the stationary distribution and the distribution at time t, proving the distance between those two distributions goes down exponentially fast. Okay, so this result was originally proven for that purpose. Okay, and the idea is that I'll go through a little bit the proof, but the proof in our own setting. But the idea is that you convert this kind of linear drift, this drift condition into like an exponential condition, and then you iterate that out, and you get some concentration, where you can prove that the probability that some Lyapunov function is bigger than z can be split into two terms. One term, which is going to correspond to the kind of burn-in period. This is sort of like, so you can think of the process consisting of two bits. One, you're really far away from stationarity, and you need some period of time to get close to where the stationary distribution usually sits. And then so that's this term, which is sort of time dependent. And then there's a second term, which corresponds to once you've hit stationarity, what do the excursions look like away from the stationary distribution? That's what this term is saying. Okay. Okay, and there's also some slightly similar results to this by Bert-Siemens, Germanic, and Cyclis, which are used quite commonly for the heavy traffic analysis of queuing systems, I think. Very similar. Okay. All right. So how does that work in our setting? So we're going to essentially look at that Hajek proof and look how we can adapt it to our case. The idea is that we're going to need two main conditions. The first condition is that we simply have this kind of net drift at some rate delta, where delta is like a non-vanishing gradient, and it's going to be proportional to alpha t, which is the step size of our algorithm. Okay. And again, because the gradient is non-vanishing, but there could be obviously this point where you're kind of at the bottom of the V shape, and obviously you can't keep going down forever. So there's a little bit of a condition here saying that when you're actually really close to the optimum, you can't keep having this negative drift. So when you're in some factor alpha of the optimum, you're not gonna see this kind of negative drift anymore. Okay. And then this is a moment condition. So you need something a little bit stronger than bounded variance. Typically for stochastic approximation, you need bounded variance for that standard DLT result. And obviously you can imagine if you're going to get exponential tails, you need the jumps of the system to be sub-exponential. Because if there were heavy tail jumps, you're just going to get heavy tail distribution out again. You're going to, you can't hope for better. So you need it to have a moment generating function, the distribution of jumps. Okay, right. With those two conditions in place, we can prove a result like this that says, I'll I'll just zoom in a little bit. If we have step sizes that are kind of some power of t, so the typical analysis is like 1 over t. This would be like what, you know, these kind of Robbins-Monroe type conditions for stochastic gradients have like 1 over t step size. So for things that are powers of t, then what we find is we have an exponential concentration where the kind of powers of t exist here in the top. Okay. And we can also argue that the distance, the respective distance of the function from the optimum is also given by that same power of t. Okay. So essentially that's saying what we wanted earlier. We said that if this is alpha t, then this should be alpha t proportional to it. Okay. So we're kind of confirming what we wanted. All right. Okay. So I'll briefly sketch out how we prove that. Sketched, so that's why it's not like handwritten. So we have this gradient condition away from the optimum. What we can argue is if we're away from the optimum, we can do this kind of, we take this term and put it to an exponential, okay? And then we just get this kind of simple bound where it's sort of like, you normally get this kind of thing when you take a random variable, it's sort of bounded above by minus the drift plus some variance term, okay? That's what this is here, okay? And then what you can do is, and I haven't written down the whole expression, but you can essentially iterate out this expression with these bounds on the top, okay? And for those of you who know like Gronwall's lemma, this is like a discrete version of Gronwall's lemma. If you're used to using Gronwall's lemma, you get something where you get the terms you're taking plus the integral of the terms you're taking producted up to t. So if they think of this as just discrete time Gronwall. Discrete Gronwall. Okay. Right. And then when you plug in actually the values of these kind of exponential bounds here, we find that you get something very similar to what I mentioned about earlier, the Hajek observed for Markov chains. So here in the stochastic approximation setting, you get one exponential term that corresponds to the burn-in. So you're kind of, that's your stochastic gradient descent starting away from the optimal point. And at some rate given by the sum of the learning rates, you approach stationarity, okay, essentially where the optimum is. And then there's a second term here, which corresponds to sort of the equilibrium excursion from optimum. Okay? So you can think of this as like drifting down from outer space, and this is giving you that tail bound. And then once you're at the optimum, these are the kind of random walk, which is determining this exponential concentration. Okay? So the two terms in the Gronwall essentially give you this. Okay? But in fact, actually, this one is for this, and this one is for this. I should have written the slide wrong way around. But okay. So that's a very high-level sketch of how that proof works, and I'll just briefly explain how this applies to projected stochastic gradient descent. So the noise condition is essentially the same as before. We just need a moment generating function for the noise. Okay, rather than bounded variance, we just need a moment generating function, slightly stronger condition. And there's a gradient condition. So normally for stochastic gradient descent on a smooth problem, this would have like a square on it. Okay. Instead, we just have just the power of the distance from the optimum. That gives us sort of conditions like this, where we see that the gradient has to be non-zero everywhere away from the optimum. Okay. It also, if we add the assumption of convexity to this condition, it corresponds to something called sharpness. Okay, so there are a number of papers on sharp functions, which just mean functions where there's non-zero convexity and some non-zero gradient at the optimum. Okay. And so there's a literature on kind of sharp functions, and there's lots of applications of machine learning problems which are sharp. Okay. Okay. And under those conditions, we can develop the result a little bit in the specific case of projected stochastic gradient descent. We can argue that the distance from the optimum is going to have the same exponential tail bound. We can argue that the distance to the optimum is going to be proportional to the step size again. And we can also look at the function values and argue that the differences between the function values are also proportional to step size. Okay? Because everything sort of is proportional to step size, essentially, all distances. Okay? Right? And as I mentioned earlier, if we looked at the standard results for stochastic gradient descent with 1/t learning rate, which is the sort of standard example that people start with, then typically this would be order square root of t, 1/square root of t, whereas we're seeing in this case it's order 1/t, so it's slightly faster convergence. Okay, so got a stronger concentration and faster convergence. Okay. So we submitted this paper. We got some feedback on a recent paper by D. Mac Davis. I can't say the last name of the other author. Zurich, thank you, and another co-author of theirs. And they picked up on an earlier paper that had proven that you can get exponentially fast convergence in the case where you've got sharpness. Okay, so in the presence of sharpness, you can prove linear convergence. They have a result for projected stochastic gradient descent that has bad dependence on the probability of convergence, but has a good dependence in terms of the rate of convergence. And then that paper has an ensemble method where they get the linear convergence with the probability and in space, essentially. And this ensemble method has sort of 3 sub-algorithms in it, okay? And that result relied on Gaussian tailbounds, okay? And so we're like, well, we've got an exponential tailbound that's more concentrated, so maybe we should just plug it in and see what happens. And what you find is that we can get the same stronger result that they had for the ensemble method, but to get that whole vanilla projected stochastic gradient descent. Okay, so we can get their strongest result with the vanilla algorithm. Okay. Okay. So how does that work? So the point is that of what we mean by linear convergence is we can get this sort of type of convergence that the iterates of the projected stochastic gradient descent to the optimum actually go down as power functions rather than it's like 1/t, 1/square root of t with high probability. Okay, so it's important that with high probability part. So you run an algorithm, it might do the wrong thing, so you run it again, it might do the wrong thing again. And you run again, and it'll kind of lock in, and then after that, it'll just go down exponentially fast. Okay.
So you're saying like the best of n trials will be extremely good.
Yeah. So if you take the number of trials, there is some probability delta, and if you try 1/delta times, you should expect to have one sample within exponent, which is exponentially concentrated around the optimum.
You'd be better off instead of running all your iterates on one stream doing this.
Doing several, yeah. So you can think of it as like a restart app. Just kind of like run it, restart it, and then you should expect one of those to output something that's very close to the optimum. Yeah.
So the high probability is 1/delta, not log 1/delta?
The original paper that I mentioned about was like 1/delta squared for projected stochastic gradient descent, and then we've improved it to be log 1/delta. Yeah, for projected stochastic gradient descent. Yeah. Okay. I mean, it's not massive. Oh, it's reasonable
I mean, they have retail, they have Pareto tail, you have exponential tail. Essentially, what you're saying is that you do it once and most likely it will work. You don't have to do it many times, actually.
Yeah,
because it is
the parameter that you can choose that you can tune to make it as likely as you like. If you knew all the problem parameters, you get this nice thing with 1/deltas. If you were willing to compromise on that, you can get it with. I'll show you the result. Maybe that's probably the better way to explain. Yeah. Okay. And the idea is that you split the this completed their proof, so I'm going to just applying our concentration method to their proof. But essentially, you split things into S stages. You're going to run the algorithm for a fixed learning round within each stage. And essentially, the idea is within one stage, you want to have half the distance to the optimum. And then you run the second stage, and then you hope with high probability you have half the distance to the optimum again. And then you keep on going like this. Okay. And as long as the lengths of the stages are constant, then you're going to get this exponential convergence. Okay. And so it's very much dependent on the rate of this burn-in period that broke down over there. Okay. Okay. And I'll add, I mean, that's very common in practice. I mean, that's what people do, don't they? They'll run stochastic gradient descent for a while. They'll see it get stuck, then they half it, and it goes down again, and half it. So, you know, it's actually quite close to what practice does. Most people don't use a 1/T learning rate in practice. So in that sense, it's all more, makes more sense in some sense.
This is equivalent to exponentially diminishing alpha. If you choose
Yes.
the right, if you
Yeah.
choose the right exponential
Yeah.
descent rate.
Exactly, yeah. So it's exponentially diminishing alpha, but you just need to make sure you keep it at that rate for long enough before you do the diminishing.
Sure, or if you like made it diminish slowly enough, you could just smooth over.
I'm pretty sure you could do that as well. That's not how we do it in the proof,
No.
just because that's easier, but yeah. One could, I expect one could do that as well.
I'm not sure if it is exponentially diminishing alpha. Are the stages all same duration?
The stages are all same duration, and yeah. So I'll go to explain. I'll give you the result. So motivation, it allows quick burn-in, and you just need to control excursions. Yeah, the first paper to do this was in 2016. This Yu and Yang paper. It's not so obvious from reading that paper that that's contained in there. So I'll give a little bit of credit to this paper as well for really clarifying this linear convergence point. Okay. So the first paper, yeah, 2016, and then there's this one. I think it's just been published in math programming, like very recently. And then, yeah, like I said, we sort of developed that result slightly. Okay, so what does the theorem look like? Basically, you have some fixed number of stages. So just to say that epsilon is going to be the error in the distance to the optimum, and delta hat here is going to be the probability that you kind of succeed, okay, in getting exponentially close. And we'll let the number of stages be sort of log 1 over epsilon. And alpha here, notice it's going to go down exponentially in each stage. So we're kind of halving it at every stage, like, okay. And the step size here is going to be fixed, and it's proportional to log 1 over delta, okay. And just to say, this delta here is drift, and the delta with a hat on is the probability. Sorry for the notation, but yeah, okay. So the probability is the one in the log, which is good. Okay, so then with probability greater than 1 over delta, we can get within epsilon hat to be optimized, and the number of iterations, so the sample complexity is like log 1 over epsilon times log 1 over delta. Okay, so that's the kind of key terms to pick up. Okay, and then we prove a slightly different variant that isn't in this paper here. So notice here you need to know all sorts of things like the kind of the width of the interval that you're working in. There's various constants that come in here from within the proofs, okay, that you don't really want to deal with. So there is a version where you allow the lengths to grow a little bit, like logarithmically, the lengths of those stages to grow logarithmically in each stage, and you slightly modify the learning rate logarithmically, okay. And the advantage of that is you just get one parameter alpha, and if that alpha is sufficiently large, then you're going to get burn-in over all times. Okay, so this one is sort of saying, like, I fix my computational budget, I fix my error, I fix the probability, and then what parameters do I need to choose to achieve that? That's what the first result says. The second result says, here's some alpha. If I choose it sufficiently large, it's just we're going to find a sample path that locks it and just stays exponentially convergent forever. Okay, so now you know the probability. This for all is inside the probability now. Okay. And the reason for doing that is actually the original proof of these guys is quite similar to the way you prove the Borel-Cantelli lemma. And the Borel-Cantelli lemma you can use to get things that happen for all times. So we just kind of do that essentially. Okay. Okay. So that just the orange text just explains what I just said. The proof is simple. At high level, yeah, you just letting epsilon be the event that at the end of the stage you half the error. Okay, and you can kind of bound the probability from one stage to the next. If you did it succeeded at time s-1, what's the probability you succeed at the next stage? And you can bound then probability doesn't work out with that our nice exponential tail bound. Okay, so here we pop in our tail bound, and then you just look at. Then you just do induction to that, and then you get some sum that's got lots of exponentials in. And you've also got the computation you require to get that, and then you just optimize the sample complexity subject to the error that you wanted. And then it's just a simple convex optimization that you solve to give the optimal choices of step sizes and alphas and everything. Okay. Right.
Just to make sure, all these results are still assuming that the gradient is not zero in the within the convex set, right?
Correct.
Okay.
Yeah. It's not. I don't think it's possible to do it where it's
Correct.
Right. Well, or there might be a comparable result, but it wouldn't be quite. I wouldn't expect the kind of same.
And the lower bounds are rates of convergence and optimization. So
Yeah. I think it wouldn't. Yeah, you really do need this sharpness. But then again, like things like ReLU functions and SVMs and other things, all have this kind of sharpness type of behavior. So it's not, or at least look in this paper. There's a whole bunch of examples where they explain ML problems, which I'm not like a big ML out and out AI ops person, but there's certainly lots of examples where they have this sharpness. So you can hope for this nice faster convergence. Okay. And you could also argue that, if you want to be within epsilon of the optimum, it's a quadratic problem that the gradient is going to be bounded above away from a certain point anyway. So you could still argue something like that. Okay. So yeah, that's this kind of sketch of the proof. Got sort of 5 minutes. So like I say, the classical results on stochastic average approximation and stochastic gradient descent have this feature that the kth iterates away from the optimum times by square root of k, goes to a normal distribution of some type, and if it's a good algorithm, this sigma should be the Fisher information. It's a statistical problem. Okay. Then the question is, well, does the same hold here, where we've got this sharpness condition? Do we have some sort of notion of some sort of optimal statistic or something like this? Okay. There's been sort of a series of works looking at this for constraint problems. There's like a paper, Ruyan, and there's been some follow-up by D. Mac Davis. So these will try to grab a little bit of some of those authors' informs just last week, and if they can look at this when maybe you have sharpness in one direction but smoothness in another, do you still have this normal approximation? And the answer is yes. And then this is sort of answering the question where you don't have smoothness in any direction. Okay. So yeah, the question to ask is, do you have exponential approximation here? And the answer is basically no, you don't have an exponential approximation. And the way to see it is just to go back to that GG1Q example. So remember, we had this workload process where you have arrivals and then you do the service. The stationary distribution of a GG1Q is completely characterized by Polacek-Khinchin formula. Okay, and that includes things like exponential distribution, geometric distribution, and a whole bunch of other things. Okay, which are not exponential. Okay, so for that reason, you cannot hope to have an exponential limit. And indeed, because the errors here are proportional to the step sizes, it's not reasonable to assume that, because you're going to be dominated by the most recent step size, which is of that order anyway. Okay, so you're unlikely to get some simple statistic like the Fisher information to characterize what's going on. Yeah, some questions.
So GG1Q, even though the stationary distribution is not exponential, if you do a heavy traffic limit, you get exponential.
Yeah.
So in GG1Q, there is no step size. It's like step size 1. But then here you are having a diminishing step size.
Yeah.
So is the diminishing step size somehow analogous to heavy traffic and can you get exponential?
So I mean, one way you could do it, you can argue things, is that once you've hit 0, if you did something where you halve the step size like before, then you could run it for a while, it hit 0, then it would lock into the stationary distribution of an excursion, and then you could argue that's not going to necessarily have the right form. So I'd argue that the counterexample that we've included in the paper is just sort of like a bit high level, like, the simplest way to see it is if these were integer valued, you can see that the support has got to be integer valued.
Correct.
And then you can argue that I can control the level of those integer values. So you can just argue that way that it's clearly not going to have one single distribution here. Mess around what the support of the distribution is, for example.
Why can't you make the same argument in the previous case, in the normal case, if it's integer valued and constant step size?
So remember here, the step size is of order 1 over k, but the errors are order 1 over square root k. So I've got room for lots of jumps in order to make a small change. Yeah. So like, you know, you can think of the process is sort of wiggling around and then like, you know, sort of Brownian way. So you're getting all these jumps to get one small change in the error. Whereas here, every transition you make is of the order of this scaling constant. You see what I mean? So you can't hope for that kind of result. Okay. That's why I said, yeah.
So in the GG1, we can prove like basically your distribution is only like multiplicatively distance from the ideal exponential, right? There are these bounds that like it's not as tight on the leading constant, but you get the same order.
Yeah,
Can we
correct.
hope to get the same thing here?
So, I mean, that's the conjecture, yes. Let's go to the next one. The conjecture is, well, what's the optimal lambda? There should be some, the conjecture is this converges to some distribution x, which is not exponentially distributed. And it's got some lambda here that determines the tail of it. And the question, which I think you're sort of alluding to there, is that there should be some optimal lambda that characterizes what happens, and that might depend on the distribution of the noise in a non-trivial way. So it wouldn't just be the first and second moment of the noise, which is what you get in the normal case. It would depend on the higher moments of the noise process. Okay.
All right, how does this get around the whole like you could tune it to have limited support thing? I thought that was arguing there couldn't be any limiting distribution.
No, it was arguing that you cannot have any single parametric form
Okay.
for the distribution here. It's going to be a messy distribution, but I'm not saying there isn't one. But I guess there probably is one. Conjecture, but and then the equivalent of saying what's the Fisher information would be to find what the optimal lambda would be. Okay.
So, yeah. Go ahead. No, I was just going to say that, so coming back to Shiva's point, that in the first case, like square root k case, your step size is of smaller order than 1 over square root k or something. That's why you get a continuous.
Yeah.
But here, your step size is kind of 1 over k, so that cancels.
Yeah.
Exactly. You get that. But all the results that you showed, they are upper bounds, right? So what if you make step size maybe fine, and then why in principle can't you have it?
Well, in all of those results, it's of order alpha.
Okay,
So if I change the step size here, I need to change that. You see what I mean?
They'll always cancel.
What about k gives the right best
Yeah.
constraint?
Yeah. So I'm just doing the 1 over k case here, but in principle, it's
No,
1 over
what
k
I
to
was-
the alpha, then there'd be 1 over k to the alpha on the front.
So what I was asking is like for 1 over k, how close you are with respect to the optimal, that is an upper bound, right? That is not an exact scale.
Yeah.
So
Correct. Yeah.
it might be that you are probably with 1 over k, you're even closer or something, like this gap is even small.
I don't know. Yeah. I don't know. I mean, it's also kind of a little bit speculative. Yeah.
So one way of thinking of the fast result is in terms of the OU process, like you explained earlier. So you're saying that the reflected Brownian motion analogy we had for this doesn't quite work, because if it worked, you would have got an exponential, and
Yeah.
it doesn't work because of this 1 over k 1 over square root of k issue.
Yeah, exactly. That's correct. Yeah. But that's not to say there isn't something like, because Kingman's got like heavy traffic stuff, which basically says you always get a certain rate out that depends on certain moments and things like this. So it's not impossible to imagine that there's some sort of optimal lambda. I haven't tried to think about it seriously, but that would be the kind of analogous conjecture. Yeah. Shall I finish my last slide and then we can grab your question?
Sorry, I didn't
No, it's
realize-
fine. It's good. I like questions.
Yeah.
I'm nearly done, so I don't want to kind of it's in the interest of time. So yeah, we can do applications. I'll zoom through this quickly, but linear program would be a natural choice because it's always going to be sharp, pretty much. Because it's always an extreme point or a set of extreme points for linear programming. So you can apply the results there. Here's some examples showing that it works. You can also use it for like reinforcement learning applications. So you can write down the joule of the MDP problem for this, and again, it's a linear program. So you could kind of think of the stochastic gradient descent doing some simple policy gradient algorithm. Okay, and again, you can get the kind of rates of convergence, which is sort of a little bit nicer than what you get in Q learning. But so you can apply things there, and here's us doing it on a simple MDP, and then there's a bottom one where we do it on OpenAI Blackjack. Okay, So just some fun numerics. Just to summarize, yeah, so we've considered stochastic approximation or stochastic gradient descent with non-vanishing gradients. We argue it's no longer Gaussian, but we're closer to something like an exponential distribution in that case. The rate of convergence is faster than what you'd expect for standard stochastic gradient descent. The proof is non-standard, using ideas from queuing. Okay, so rather than using, we don't use smoothness, we're not using convexity bounds or anything like that. We're using something more direct. There are some nice things that you can say. You can say that you can improve some of these linear convergence results for projected stochastic gradient descents. There's nice consequences. There's obvious questions around the normal limit and the exponential limit in this case. I've discussed a little bit the conjectures and counterexamples around that. And you know, the results are applicable potentially to fun examples in ML, NDPs, RL, things like that. So it's just they're just kind of fun examples. I'm more interested in the theoretical point here. Okay, and that's it. Thank you for listening.
Yeah, so the thing I was thinking about was, okay, so whenever you're trying to find the stationary distribution of a GG1, we know that it's got this sort of ugly form if you're trying to find the exact stationary distribution, and
Yeah.
you have to go down this like Weiner-Hopf factorization method, which like never works out nicely. Do we sort of expect the true limiting distribution to look something like that for this system, or is there reason to believe it's like nicer than that?
I think for the 1D case, then yes. But then most problems are high dimensional, and then it just is anyone's guess at that point.
Because you're like reflecting off of many different patterns.
Yeah, exactly. Yeah.
Then there's the, you know, the nice case of that world is when you have an MG1, right? Which is when essentially when the negative part of your drift looks exactly exponential.
Yeah.
Do we have any hope of that? Like if we chose the right, I don't know, stepping rule, that it would be nicer?
Like there could be nicer versions, and I think niceness in the noise process would correspond to niceness in the very high
It's
level.
like if we had, it's like we had one directional noise basically.
Yeah.
Okay.
Certainly the things where we're expecting, like a queuing process, we're expecting some noise in both directions, getting back to Schill's point, we're expecting that there's a positive probability actually away. There's a positive probability in. Yeah. And obviously if the support of the process was always negative, you always
Well, that'd be
towards
better.
it, then
That'd
you
be
know
better.
you'd be much better than exponential. So that's why I haven't gone in too much into lower bounds or things like that here, but you know. You can already see that if you have a positive probability of jumping away and the size is alpha, you can kind of see that you're going to have to be order alpha anyway. So I didn't go too much into that, but there are points of that nature. Yeah.
Did you say that you get 1/k rate of convergence in reinforcement learning?
Yeah.
But there are statistical lower bounds that say you cannot beat 1/epsilon square.
Yeah, but there's a minimax. So in the non-minimax case, it's a bit like a bandit problem. If you know what the transition rates, you get like a delta, 1/delta times.
Oh, you know the transition rates? Yeah.
Well, here that bound is going to depend on the angle where you go to the optimum. And if you took the minimax version, where you try to optimize the angle to make the worst case scenario, yeah, you go back into those kind of cases.
I see.
Yeah.
What you're saying is the bad scenarios are all the vanishing gradient scenarios. And like if you don't have vanishing gradient, it just isn't that, it isn't that adversarial.
So an analogous, by analogy, so you took an bandit algorithm. There are log t regret bounds, which would be like the changes 1/t.
It depends.
And there are square root of t regret bounds, which are like the worst minimax worst case.
I see.
So the reason we get 1/t here is because we're essentially known.
So what's the analog of delta here?
Delta is the angle at the sharpness point. So I could imagine if I knew I was going to run an algorithm for a time t and I chose the worst case angle at the optimum, then it might.
So what is this angle in an MDP?
Well, so when I'm talking about the sharpness of the function, I'm talking about here's the optimum here. Yeah, remember it's a linear program, and the angle is basically the gradient.
So this x star is supposed to be at a corner point, right?
Yeah.
Oh, so this is the angle at that corner point.
Yeah, but like like in a regret setting of a bandit algorithm, you'd have a dependence on this delta. And then if I optimize this delta to give me the worst case bounds, it would be
Then you get
very
it. Right.
Yeah, so then we're not contradicting that because bounds in the RL was just square root of t and minimax lower bounds, like these are minimax bounds. Yeah. So the point is the delta here is sort of that angle here.
People even did this instance dependent bounds.
Yes, it's
But
an
still-
instant dependent bound.
Okay,
So
but I've never seen instant dependent bounds that are 1 over t in RL.
Yeah,
I
they
thought you were
exist.
doing
Yeah, I
that.
think UCRL would be an example that has 1 over t. Because UCRL is log t regret, for example, so that would be an instant dependent bound that gets that.
Ah,
So it's definitely not like proving something that can't be proven. I did check that, yeah. Yeah.
Just looking at your open problem, seems like maybe you can do like some kind of coupling arguments, then possibly that, well, if you are hoping for it to be an exponential tail, you come up with a different process which has a nicely behaved noise and stochastically dominates your original process, and it's easier to deal with.
Yeah, okay, so yeah, the first version of these results, I did a proof that was mimicking Kingman's proof, which is that, and similar to that, yeah, I kind of tried to bound the iterative process above by an IID process, and then use Linley's recursion, and then try to prove it that way. And you can get something there. But then you have to make weird assumptions, and then I found the Hajek proof and thought, well, actually, that's a lot nicer, so we'll just use that instead. But yeah, you can approach it from the angle with a coupling argument. Yeah, it's possible. Okay, thank you.